So let's start analyzing this data set. What we're going to do is we're going to get this as a data frame. We've already got the data, and we already saw that using the frame attribute, we can get the frame object from this data. Right? So we can do df is equal to data.frame, and we can inspect what it looks like using the head attribute, using the head method. The head method will give us the list of first 5 rows in the data frame. This is df.head. Optionally, you can specify how many rows you want. For example, df.head10 will give you the list of first 10 rows from this data set. But if you don't specify anything, then by default, the head method will give you the first 5 rows from this data set. Right? So this will tell us what are the columns in this data set. So we have the season, which can be spring, summer, autumn, winter. Then we have the year. I think 0 corresponds to 2011 probably, and 1 corresponds to 2012. But we can take a look at what are the values each of these columns take. And there is month, hour, whether it's a holiday or not, whether it's a weekday or not, whether it's a working day or not, the weather, temperature, what the feels like temperature. Often in newspapers or in your weather app, you would see something like temperature and then feels like. So this is the feels like temperature thing. This is humidity, wind speed, and then this is finally our target variable, which is the count of the basically the number of users who are using that bike sharing service on any given day, right? So here let's inspect this a little bit further. So let's get the y variable and the x variables, that is the features, separately. Let's separate the features and the variables. So we're going to do y is equal to df. We've named our data frame as df. So y is equal to df count will just return that particular column, and x is equal to df dot drop. We're basically dropping this column count. But if you don't specify anything, it will search for a row named count, which is not what we want. We have to specify that axis is equal to 1. And just to confirm that we have done this correctly, we will check the shape of the x and y after we have done this separation. All right. So before we did the separation, I think we should check that also first. So df.shape was 17,379 rows and 13 columns. Now it is 17,379 rows, the same thing, but 12 columns for the X dataset and basically just 1 column for the labels. Okay, so now what we're going to do is split this into train and test sets. So generally, when you are working with ML projects, you will, especially on Kaggle or something, or in any competitive setting, you will be given a train set and a test set. You will be given access to the features of the test set. However, you will not be given access to the labels of the test set. Here we are not provided with separate train and test sets in this OpenML dataset. So this is something that we have to create by ourselves. We have to make the split by ourselves to ensure that our model is performing well. Because otherwise, we could get a performance of 99% or 100% on the train set, but it doesn't mean anything if we don't have any test set to verify how well our model has actually learned to generalize and not overfit. Right? So we are going to start off by separating the train and test sets immediately, and then we will completely set aside the test set and we will not be looking at it except for the purpose of evaluation. All right? So we are going to start by importing train test split. This is part of sklearn's model selection API. Import train test split. So we will split it into the train data frame, test data frame is equal to train test split from the original data frame, and then you specify the test size. Alternatively, you can also specify the train size, and the other one is just taken as 1 minus whatever you specified. And random state is just something so that in different runs of our notebook, we will be getting the same split. Otherwise, the split will change for every run of your notebook. For it was just a number that everybody picks. So I'll just go with that here. But you can pick any number of your choice. Because generally when you're working with ML projects, say on Kaggle or Google Colab or something like that, in basically in a notebook environment where you will have to run these cells multiple times. Like let's say you do something today and you go back for a few days and then you come back and work on it a few days later. You don't want the data set to change every time, right? So for that purpose, we'll have this, we'll set this random state for the purpose of reproducibility. Okay, so we're making the split and then we will just test that it has done the split correctly. Train df.shape, test df.shape, and it has split it into 13,903 and 3,476. All right. So what we're going to do now is split this train and test data frames into further x train, y train, and x test and y test. So we're going to do y train is equal to train df count, just the count column, and then x train would be train df dot drop. We want to drop the count column and we want it to be dropped from the columns, right? Similarly, I want to do the same thing for the test set also. Let's do the same thing. X test and Y test, but we want to drop it from the test data frame. Yeah, that should be good. Let's do this and let's check that Y X train. Let's just check X train dot shape, X test dot shape, Y train dot shape, and finally Y test dot shape. We should have 12 columns in the train sets, and we need 13,903 rows in the train set and 3,476 rows in the test set, and these are going to be the same number of samples but with just one column each. That should be the expected output, and it is the expected output. So we can go ahead into now setting aside the test set and then purely working with the train set here on after. All right. So we are going to look at a method called xtrain.info, the .info method basically. This method tells you the amount of non-null entries in each column. So you have 13,903 entries in total, and in each column you can see that all the entries are non-null, which means there are actually no missing values in this data set, and that makes sense because this is data collected from presumably a smartphone app, right? So it's quite natural that there shouldn't be any missing values because this is just data aggregated from the smartphone app. And it also tells you the data type of each column. As you can see, categories is a categorical column, and if it says object, it doesn't say object for any of the columns here, but if it says object also, it generally is a categorical column. And here you have int64 and float64, and these are your numerical columns. So int64 is integers and float is the decimal point, floating point values. All right. And it also tells you that this data set has occupied 1 MB of memory on our RAM, right? There is also another method called describe. So this describe method will tell us for the numerical columns alone some measures like mean, median, mode. Right. Next, we'll look at the describe method, and this describe method will tell us some descriptive statistics for each of the numerical columns. Note that this is only for the numerical columns. So this describe method, it takes only the numerical columns. As you can see, you don't have these category columns like season, a holiday, working day, weather, these columns are not there in this in the output of this describe method. And for each of those columns, you have the count, which is the total number of rows in each of those columns. Then you have the mean, the standard deviation, the minimum value, the maximum value, and then the first quartile, the second quartile, which is also known as the median, and the third quartile. Okay, so this can sort of give us some idea about the scale of this data. All right, so let's also do this for the labels. Describe. And here you can also see the descriptive statistics for the y-train variable, for the y-train, that is the target variable. And you can see that the mean of the target variable is 190.57. So about 190 to 191 riders. So on average, about 190 to 191 people use the app on a daily basis on an average day. But the standard deviation is very high. The standard deviation is 182. So just think about this, just one standard deviation away, and 190 minus 182 is 8. So just one standard deviation away is only 8 people using the app on a daily basis, right? On the other hand, I mean, of course, it's impossible for a negative number of people to use the app on a daily basis, or on any. I mean, it's impossible for a negative number of people to be using the app at any point of time. So this means that this data set is likely to be a bit more left skewed, right? Because you can have multiple standard deviations above the mean in this case, but while also not having too many standard deviations below the mean. Okay, so this is going to be, before we actually start observing this data set, we can conclude that this is going to be something like a data set like this with a long tail on the right. Okay, so we can plot this. We can plot this and see. We'll be using matplotlib and seaborn for this. Import matplotlib.pyplot as plt and import seaborn as SNS. So what we're going to do is we're going to use a histogram plot, sns.histplot, and we're going to be using the data as y-train. Okay, and then plt.show. As you can see, our prediction was right, and we do in fact have a long tail on the right side, which is natural, because even for one standard deviation, we had it go down to 8 days, which obviously means that you cannot have 2 or 3 standard deviations on the left side, which means that most of the standard deviation should be from the right side, which is what gave us this conclusion, and that is what the graph shows us as well. Okay, probably we can make this a slightly smaller picture. So we can have plt.plot. Big size is, let's say, 10,4. Let's see what that looks like. Okay, so it's a slightly smaller picture, fits on the screen, right? Now, let us also look at a box plot for the distribution of this target variable. Okay, so we have sns.boxplot. In our box plot, we can actually see that most of the data is centered in this region. So this actually represents the lower quartile, that is the first quartile to the third quartile, and this middle line is the median. So it shows that on the median number of users is also somewhere around 170 or 180, and most of the users are centered around this, probably something like 30 users to something like 270 to 280 users probably, right? But it also does have a lot of outliers, which is what is shown in this region. So this is probably this is probably the outlier interval, that is the upper bound plus 1.5 times the interquartile range. Generally, that is the criterion for considering a point as an outlier. So beyond those, every point beyond that benchmark are considered as outliers, and this is the set of outliers that we have. So as you can see, we have a large list of outliers actually. We can also look at a violin plot for this. So what we can do is we can plot the box plot and the violin plot side by side. So the way to do that is to do something called axis is equal to plt dot subplots. So this is the way to get subplots, and we want one row and we want two columns side by side, and we want the figure size to be, say, you can keep the same thing, 10, 4, right? And we have SNS dot box plot data is equal to y train, and we want this to be the first picture. So that is the 0 index, right? And we can set the title for that, axis 0 dot set title. We can have the title as box plot of target variable count. Target variable count. All right. And next, for the second plot, we can have, say, SNS dot violin plot. The same thing, data is going to be y train, and this is going to be on axis 1. 1 dot set underscore title, and this is going to be a violin plot of the target variable, which is count. All right. So we don't want this. So the way to do that is to write plt.show. So it renders it as a proper picture. Yeah. So now you have the box plot and the violin plot. The violin plot somewhat shows the amount of values in each of these intervals. Like you can sort of think of it like the density of the values in each of these intervals. And so this is the box plot and the violin plot side by side. These are generally used to see how much the data is skewed and in what interval majority of the data lies. So these are two commonly used plots for that purpose. Okay. So that's the box plot and the violin plot. Next, what we'll be doing is we will look at some of the features. We'll look at some of the features and try to see if we can get any sort of interesting insights from the features. Okay. So as you can see, the features are, you have season, which is a categorical feature. Then you have the year, the month, and the hour. So year is probably not a very useful feature here, because remember that the year here is 2011 and 2012, right? So that's the years from which this data has been captured. Now, by definition, if this so let's say that there is some correlation that we find between year and the number of people who are driving or who are riding the bicycle or who are using the smart bike sharing system. Okay, let us say that we find some correlation between these two things. Now, is this useful for us? It's the next question. Okay, because let's say I'm using this data in 2013 or 2014, or maybe even in the current day in 2026. Right? So let's say I'm trying to predict in 2026 how many people are going to be, I've learned a model and I'm going to try to predict how many people are actually using this bike sharing service on a particular day, given various given information like, what is the season, what is the month, what is the hour, and so on. Now, the year isn't going to be of much help here, because it's going to be either 2011 or 2012 as far as our training set is concerned. And that might work on the train set and on this particular test set because that is also from 2011 to 12. But if I try to use it in a real world type of setting, it's not going to be helpful at all, because by definition, any data that I'm going to use today is not going to be from 2011 or 12, right? So this year column is actually completely uninformative. And in fact, it can it can actually end up giving us wrong inferences from the data. If we find out that year and the count variable are actually somewhat correlated, then and we try to incorporate that into our actual model and start making predictions on it at test time, at actual, when you actually apply this in a real world setting, then this can actually go drastically wrong. So we will actually be dropping the year column. We can still look at what it's like and whether 2012 is higher or 2011 is higher and all that. So we can do all that exploration, but in a real world setting, we are going to actually be dropping that variable. Then you have the month, hour, holiday, weekday, working day. So this actually looks interesting because it's either a weekday or a holiday, right? So why do you have both of these things mentioned? So that's something that's interesting. We'll explore that in a little bit more of detail. And so then you have weather, and weather is a categorical column. Presumably you have a few categories like windy, breezy, sunny, rainy, etc. Then you have the temperature, the field select temperature. These two look quite similar. So we'll look to see if there is these columns are highly correlated. It most likely should be highly correlated. And then you also have humidity, and then you have the wind speed. Okay. So if these two columns are correlated, then we'll probably drop one of these columns, because you don't want very highly correlated columns in your data set that can actually distort your model. And so we might drop one of these columns. We'll have to explore that a bit further. But for now, these are our columns, and let's take a look at, let's try to see if we can get some meaningful data from these columns. So let's plot them and see what it looks like. So we are going to start with some of the numerical columns here. We're going to in fact start with temperature, humidity, and wind speed. Okay, we're going to start with temperature, humidity, and wind speed, and then probably we'll look at some of the other columns. I feel these are some of the most important columns. Of course, the field's temperature is something we'll explore later. We'll start with temperature, humidity, and wind speed and see what is the distribution of these columns looking like. Okay, so we will do this similarly in using the subplots thing that we just saw. So we will make, let's make one row with 3 columns, and we will have the figure size as say 12,4. So the first plot is going to be a histogram plot. All of the plots are going to be histogram plots, and we want the temperature column, right? We want the temperature column, that's our data. And what we can actually do is set this on the very first, set this as the first picture, and we can set different colors for each of them to distinguish it properly. You can have color is equal to say sky blue. All right. And we can set the title for this, set title as distribution of temperature. All right. Now we can actually copy that and use it for the other two as well. This is going to be the second one, is going to be for humidity, the histogram plot of humidity, and this color, let's set it to something like olive. All right, so this is a light yellowish green color, and this is the distribution of humidity. And our last plot is going to be for wind speed, and let's set it to say green, and this is going to be the distribution of wind speed. All right. So we can make it a tight layout and plt.show. Okay, so that's given us uh, the histogram plot of each of these things. So temperature it doesn't look skewed. It somewhat does look a bit like a normal distribution, but there are these spikes in the middle and this little bit of a down spike in this particular region. Well, maybe that's just for this particular data set that just maybe there was nothing that was exactly 20 degrees or exactly 19 degrees, right? But it does somewhat resemble a normal distribution when you look at it. And then there is humidity. So humidity does have a bit of a skew. So humidity, notice that humidity is actually restricted to between 0 and 1, right? So because 0% is probably where the air is completely dry, whatever that means, and 100% is probably on rainy days where the air is extremely humid. So humidity can only take on values between 0 to 1, which is between 0% to 100%. And then you have wind speed, which it does look like most of the time the wind speed is, say, less than 20 kilometers per hour. I'm assuming this is in kilometers per hour, and there are very few observations where the wind speed is much beyond, say, 30. Right? There are a few instances where the wind speed is extremely high, so this could probably be something like a cyclone, I'm guessing, or a storm. But one interesting thing to note is that there are a uh, lot of instances where the wind speed is exactly 0, but there seems to be some missing gap here. It seems like the wind speed isn't properly picked up until it touches, say, 5. So this could possibly be explained by something like a wind sensor. So the way these wind sensors are set up is, based on the movement of the sensor, depending on the wind speed. So it could be something like, when the sensor doesn't move at all, maybe it takes a little bit, so maybe it takes like 4 kilometers or 5 kilometers of wind speed to actually make the sensor move a little bit, and that's what detects it. So anything below that 4 or 5 kilometers per hour is not picked up by the sensor at all. So that could potentially explain this gap between 0 kilometers per hour to 5 kilometers per hour, say. So everything between 0 to 5 kilometers per hour is just captured as 0 kilometers per hour. So that could potentially explain the gap here in this wind speed. Now, one thing we can do is we can use these histogram plots to get some sort of density estimate for each of these distributions. So the way to do that is to set something called KDE. KDE stands for Keep Density Estimate. By default, it is false. You can set it to true. And let me do that for each of these. KDE is equal to true. Let me do that here also as well. And this will plot a density curve for each of these plots. So as you can see, so it has plotted a nice density curve here. This does resemble a normal distribution, and here it does look like somewhat a skewed distribution that abruptly stops at 100% naturally, because humidity cannot go beyond that. And here you do see this drop, but if you ignore for that and somewhat adjust this 0, you can probably see that it's constantly decreasing, almost monotonically decreasing distribution here for wind speed. All right. So that's what we have observed from temperature, humidity, and wind speed. Now let's see how some of the other variables look like. So now let us see probably the seasons, right? So let's see what are the seasons that are there in this data set, and let us look at the box plot for the seasons. Okay, so let's look at the season variable. So df season dot value counts. So this value counts method will give us the number of occurrences of each value that this particular column takes. So there are 4,496 instances of fall, 4,409 instances of summer, and then spring and winter in this data set, right? And we can actually look at how the what is the demand on in each of these seasons, the average demand, and then sort of like the minimum and maximum demand for the bike sharing service in each of these seasons, and whether it plays any role, right? So this is something that we can observe. So we can use the box plot for this. We can say data is equal to train df, and on the x-axis we want the season, and on the y-axis we want the count. So notice I'm using the train df for this, not just xtrain. The reason for that is because we want to use both the x and y variable in this. So we want to see if there is any relationship between the y variable and the season variable. Okay, so here we have count, and let's assign a palette is equal to variedis, and which is one of the most common palettes in Matplotlib. It's a nice palette, and you have to set the hue season. You can still Matplotlib will throw an error. I mean, it will throw a warning actually. It won't throw an error if you don't set this hue is equal to season, and it will say that it's deprecated. It'll still work, but you'll get a warning. But you know, why get warnings? So, all right. So this is, maybe we can make this a tiny bit smaller. plt.plot page size equal to 10,4. Probably plt.tight layout. All right, so this is our box plot for the seasons. And one thing that might actually be surprising when we see this plot for the first time is that the median and the average itself of the number of people who are using this service is actually very low in spring, and it seems to be very high in summer, fall, and winter, right? So this might be a bit surprising, because you might think, like, I mean, if without looking at this, if you want to come to some conclusion, generally you would think that spring is a very pleasant time to be riding bicycles around, and probably winter is not such a good time to actually be riding your bicycle around the place. And it's probably a terrible idea to be using the bicycle so much in winter. So I looked into this, and it turns out that the way that this data set has actually been labeled is that the months Jan to March actually correspond to spring, and April to June corresponds to summer, and then September to July to September is fall, and October to December is winter. So that's how the authors of this data set have actually segregated the seasons, and they have not done it based on the temperature. So in many parts of the world, and specifically in Washington DC, so you can actually look at Washington DC temperature by month, and you will actually see that in December, January, and February, the temperature is very low. So probably December, January, February is corresponding to winter, and then March, April, May should be spring, June, July, August should be summer, and then September, October, November should be winter, right? So if you go by this graph. But that's not the way that this data set has been labeled, and that's the reason why we see that spring actually has such a low such low demand for this bike sharing service. But in any case, the way that we are going to be using this but in any case, the test data set is also going to be labeled the same way. So at least for the purpose of this data set, we are not going to run into a problem with this. But it's something to keep in mind. Sometimes you might think that you come across such things which are a bit counterintuitive, and then you can dive a little bit deeper into the data collection process and things like that, so that when you actually run the model in a real world setting, you might label spring, summer, fall and winter in a different way, and the data set in which you are actually using for the purpose of training the model might have labeled the spring, summer, fall and winter in a different way, and then those two won't match, right? So that's something that you have to keep in mind, especially when transferring this to a real world setting. Okay, so for our purpose it won't matter much, but it's just interesting to note that there definitely is some strong correlation between the seasons and there is definitely some strong correlation between the seasons and the demand for this bike sharing service. So as you can see, fall has the highest average demand for the bike sharing service and spring has the lowest, and summer and winter are actually quite close by, and they have roughly the same median demand and roughly the same distribution of demand, right? So now let's also do this let's do a similar exercise for the weather variable. So we have, let's do the same thing for the weather variable. Exercise 10 4 train df, we will have weather, found palette is hue is weather, right layout plt dot show. Yes. All right. So weather is categorized into four, that is clear, heavy rain, misty and just rain. So it turns out that there are very few observations of heavy rain in the data set, at least that's what we can gather from this data. And for clear, misty and rain, there seems to be more data, and generally in clear skies you see the highest average demand for this bike sharing service, and even when it's misty you have quite high demand for this bike sharing service, whereas when the weather is rainy you see that the demand really drops. And of course for heavy rain also it seems to be the case that for rain and heavy rain probably we can merge this into a single uh, we can merge this into a single value if it is necessary, but we can see that the average demand when it is rainy is actually quite low for this bike sharing service, whereas when the skies are clear or when the weather is misty but not rainy, there seems to be a high demand for this bike sharing service, which is pretty much what we would expect, right? So nothing surprising there. All right, so that's about it for the categorical variables. Now, I think we've covered most of the categorical variables. Now, there are some true or false, that is Boolean variables, that we will be coming around to. Now, before that, let's look at the numerical variables. So let's plot a correlation matrix for this. What we will do is we will select the data types, and we will specify include is equal to number. So this will automatically select all the float columns and the integer columns. Dot cor does the correlation. This gives us a correlation matrix. What we want is a heat map. This correlation matrix was actually this outputs a matrix, but if we want it to be colored, in red and blue and all that, so the way to do that is to use a heat map and then pass this correlation matrix as an argument to that heat map. So that's what we'll be doing. We'll pass the correlation matrix to this heat map and we will say annotations is equal to true. So that will actually give us the values of each cell rather than just giving us the colors. And the standard pattern is to use school warm, which means the range is from red being highly correlated to that is the deep or dark red being highly correlated to dark blue being very low correlation. And we want two decimals, so that's what we'll be using, dot 2f. Then we have plt dot, let's set the title to feature correlations, plt dot show. So that has given us this heat map, and we can ignore the diagonal columns. Obviously, every column is correlated with itself. That's quite natural. But apart from that, we can see that this field temperature and temperature column is very highly correlated, which is something we did expect at the start, right? So naturally, temperature column and field temperature column should be highly correlated. Generally, if the temperature is say 28 degrees, then the field select temperature is probably also around 28 degrees. Maybe it's 27, maybe it's 29, or maybe it's 26, something like that. But it's definitely not something like the actual temperature is 28 but it feels like 50 or it feels like 40. That's not going to happen, right? So generally you do expect that they are going to be highly correlated. Let's look at some of the other interesting correlations. So you have what is this? You have count and temperature being highly correlated, and naturally that also means that count and field temperature are highly correlated, which actually is interesting because it means that depending, so we did see that based on the season and based on the weather, that actually heavily impacted the average demand on that particular day for the bike sharing service. And as a natural extension of that, we are also observing that this temperature column influences the average demand, right? And another interesting thing is the hour. The hour column also has a big impact on the count. So that is something that is interesting to note in this particular case. Naturally, probably you expect that there are certain times like the morning time or the evening time where the people use these bike sharing services to commute or for relaxation or recreation purposes, and probably the demand might be lower during the middle of the noon or the afternoon or something like midnight. But that's something that we should observe the data and see what it's like. There is heavy inverse correlation between humidity and count, which is the demand. So this is also somewhat understandable because when when the humidity is high, it means that there is a high chance of rain. When there's a very high humidity, it probably corresponds to days on which it actually rained. And as we have seen from the weather column, the days on which it rained are days where the demand for the bike sharing service was low. So this makes sense. And similarly, on days where the wind speed was too high, presumably it's difficult to cycle, so it's difficult to pedal. So wind speed actually seems to have a strong negative correlation, somewhat decently strong negative correlation with humidity. Okay, so that's something we can keep in mind. And there is hour and humidity. So hour seems to have a somewhat negative correlation with humidity. Okay, that's interesting. And I guess that's about it. That's all the major that's all the major correlations. And one more interesting thing is year and count do seem to have a positive correlation of 0.26. But as we have discussed before, this is a very bad idea to take here. This probably just means that in 2012 the average number of people riding or using the bicycle service on any given day is higher than the average in 2011. Since this data set is only for 2 years, 2011 and 2012, it probably just means that the average in 2012 is higher than 2011. That's just about it. So it's best to drop this column and not try to get any serious inferences from this particular column. Okay, so that's what we have inferred from this correlation matrix. And so that's most. So we have seen the numerical features, we've seen the categorical features. Now let's look at the Boolean features. Okay, so the Boolean features in this case are holiday, weekday, and working day. So these are Boolean features, and let's see what inferences we can gain from these. So what we're going to do is we're going to try to see whether if a particular day is a working day, whether that actually affects the demand for the bike sharing service. On the other hand, if the day is a holiday, does that seem to show any demand for the any patterns in the demand for the bike sharing service? Okay, so let's plot those side by side. So let's plot holiday and working day. Okay, so subplots. So we're going to use bar plots for this. Data is equal to train df as usual. X is going to be holiday. And we're going to try to study the impact on the count, which is the target variable. We'll have a muted palette for this one, and which for binary bar plots, that'll just give us some light pastel shades of orange and blue. Okay, axis equal to axes, and we'll have our second bar plot, and this is going to be for working day. We have the same muted palette, and we want this as the second plot, that is index number 1. Okay, all right, so we've got a warning. Yeah, so this is the warning I was talking about initially. So we need to set the hue variable. When we're setting palette. So we can just say hue is equal to, of course it still works, but just give us a warning, which I don't like to see. So let's set hue to holiday. And here we can set hue. Seems a bit redundant actually, but that's the way they have Seaborn has refined their API, so there's nothing that we can do about it. Okay, sorry, this is not holiday, right? So this is working day. Working day, hue is equal to working day. All right, so we've got the two plots. So if it's a holiday, and if it's a holiday, true. So if it's a holiday, you see that there is actually a lower demand for bicycles on a holiday. Okay, and on a working day there is actually a higher demand. I mean, on a non-holiday there is actually a higher demand for bicycles. On the other hand, you see that on a working day there is a higher demand for bicycles, and on a non-working day there is a lower demand for bicycles, although this distinction seems to be a lot lesser. So you would assume that the opposite of a holiday is a working day, correct? But that doesn't seem to be the case, because if that were the case, then these two charts should just be the mirror image of each other's. So it's basically it should just be flipped versions of each other, but that's clearly not the case. So what we'll do here is we'll probably also plot weekend here, right? So we'll make this 3 columns, and let's plot the weekend here. So this is going to be weekday. I think it was weekday. Let's just quickly check that. Go to 2. Yeah, we'll add that to our. Okay, so weekday is basically the day of the week. So weekday is not just whether it's a weekday or a weekend. Weekday is also the day of the week. All right. So one thing that we have to note here is I actually did a little bit of research on this as to why these two are not the same thing. And it turns out that it's mentioned in the dataset itself that for the specification of working day, if the day is neither weekend nor holiday, then it is 1, otherwise 0. So basically it's a working day if it is neither a weekend nor a holiday, right? And for holiday, they've actually given whether the day, okay, I mean, it's a humorous mistake here. It should be WHET we're going to create a new column called day category in this data frame, and it's going to be dot apply this function get day type, and you want to do this along the columns. So it's a new column that we're creating, so access is equal to 1. All right, so now let's execute this, and then let's plot this. Okay, let's plot this. Be a smaller figure, let's say 8 by 5. All right, and we want a bar plot. We want a bar plot, sms dot bar plot. We want the day category. So we want this for a training data frame, train df, day category, and y is count. It is a target variable, right? And yeah, we can probably go with palette, can be anything. Probably we can go with muted, right? Then so we'll get a bar plot. Basically we can set a title for it. Average rentals on work day versus weekend versus holiday, right? Yeah. Then we have plt dot show. All right. Okay, so this is a warning. So we need to set hue is equal to day category. Day category. All right. So okay. Okay, that gives us everything this well. Okay, it's true or false. I have given true or false. Let's try 1 and 0 problem. No, still the same thing. That still gives us this single. Everything is classified as workday, which clearly means that it's not recognizing this to be holiday. I mean, it is true and false. It does say true and false here. Clearly it is true and false. It's not working. Okay, let's look at type of column here. Holiday, and that's the catch. See, here it says category, right? So here it says category. It doesn't say boolean, or it doesn't say integer or something like that. It says category. And if it says category here, then it almost always means that this holiday and this working day are actually strings. I mean, their values are strings, which means that this true and false that we see here are actually not the boolean labels true and false. These are actually strings. These are actually strings. So df working day dot value count, these are actually strings, and these are also holiday, whatever we got for those are also strings, right? So which means we should probably put quotes around this, and hopefully this should now work. Yeah, we have to change this. All right. Right. Okay. Yeah. So that was the issue. The issue was that we had set it as we are not. I mean, it looked like it was boolean, but it was actually string, and we had to add the quotes around it to pass the string. Right. All right. So this is average rentals on workday versus weekend versus holiday. So as you can see, on holiday, the average rentals are quite low. The standard deviation is a bit higher than for the other cases. Maybe there are lower number of entries or whatever the case may be. But on holiday, the average demand on holidays, the average demand for the bike sharing service is actually considerably lower. Actually, this is around 150, whereas these are both around 180 to 190 types, right? So there is a considerable difference in the demand. So there is at least 35 to 40 units of difference in demand, which is quite substantial, right? And this is interesting to know that uh, weekend and weekday seem to be somewhat similar. There seems to be a similar amount of demand on irrespective of whether it's a weekend or a weekday. But if the day is a public holiday, like July the 4th or whatever be the case in America, like this list of holidays, whether it's New Year's, Thanksgiving, Christmas, and for these public holidays, the demand seems to be considerably lower. So this is something we can actually investigate. Maybe we can look at, maybe one possible explanation could be that on weekends, people still commute for recreational activities, and on work days they probably commute to work using these bike sharing services. And on holiday are probably like something like a family get together or things where it's a more of a family or community type gathering. So probably not much use for bicycles, which are single person mode of transport. That could be a possible explanation, but I think if we do an analysis where we look at the time for each of these things, so maybe there is a different time that people commute on the weekends, maybe there is a different time that people commute on the work days. For example, if it's for recreational purposes, then we would see something of a different time here, whereas on work days we'd probably see morning and evening or late evening type stuff for work days. So that's something that we'll explore in subsequent episodes of the series. So this is the first episode, and uh, hopefully this sets the tone for the future episodes to come. This is the type of analysis that we have to do. So we always formulate a hypothesis. Maybe it's due to this reason, maybe it's due to that reason, and then actually verify if if the data actually backs it up. And if that's the case, then probably we can come up with some sort of explanations as to why that is the case, right? So this is the process of exploratory data analysis. So we've explored the numerical variables, we've explored the categorical variables, we've also seen the Boolean variables, and we've also seen how to convert a couple of variables into this new column. So this is probably the first example that we're seeing of feature engineering, where we created a new column called weekend, workday, and holiday, and we got some insight. So we originally had this, which we saw that there was some discrepancy between these two. Then we went and found out the reason for that here, that what is a working day and what is a holiday. And we combined these two columns, and now we have actually got a much better understanding of the distribution pattern on weekends, workdays, and holidays. Right? So that's about it for episode 1. We'll continue the series in episode 2. So stay tuned for that. Cheers.